Let's talk about volumes by slicing. So we're going to be trying to calculate volumes of three-dimensional solids, and we need to define a few terms first. So we define the cross-section of a solid to be the intersection of a plane with the solid. A cylinder is defined as any solid that can be generated by moving a plane region along a line perpendicular to the region. This is called the axis of the cylinder. Thus, all cross sections of a cylinder are identical. Okay, so many of the cylinders that you might be used to might look something like a circular cylinder. So if you have a circular cylinder, that's going to look like the cross-sectional area is a circle, and that runs perpendicular to this axis. Okay. You could also have a cylinder where the cross-sectional area is not a circle. So you could have something, for instance, where the cross-sectional areas are triangles. So I'm going to try to add an angle so that you can see that it's got a little bit of perspective. And then, this type of object here, this is also called a cylinder, even though it's not circular. So in this example over here, the cross section is a circle, but in this picture over here, the cross section is a triangle. All right. So to calculate the volume of a cylinder, we multiply the area of the cross section by the height of the cylinder. So our volume V is going to be equal to the cross-sectional area times the height. All right. Now, in the examples that I drew up above here, the cross-sectional area of a circle and the cross-sectional area of a triangle, these were constant throughout the whole shape. What we want to do now is we want to consider the following case. If the area of the cross-section is not constant, we may not have a formula for its volume. We will need to use a definite integral to calculate the volume of this solid. So there's two key ideas here. The first key idea is that the cross-section is not constant, and the second key idea is that we're going to set up a definite integral. So the way we're going to do this is we are going to chop the solid, or chop up the solid into pieces, estimating the volume of each slice, and then we're going to sum those estimated volumes together. The slices should all be parallel to each other, and when we put all the slices together, we should get the whole solid. So let me try to draw some examples of the situation to show you. So if you look at this picture on the right, I have this axis that the solid lies along, but when I look at each cross section of the axis, I get a trapezoid. So the cross section is going to be a trapezoid, but do you notice how the trapezoids are getting bigger and bigger and bigger? So what do I do? Well, I am going to have that my cross section is going to be a trapezoid. So let me draw a trapezoid like this. And the cross-sectional area of this trapezoid, it really depends on x. So I'm going to put an A of x in order to highlight that fact. So if you look at our picture here, if our area is evaluated at the point x0, this has a much larger cross-sectional area than if we evaluate at x3. This is a much smaller cross-sectional area. All right. The other thing that we're going to notice is that we're going to slice this, this solid up into very thin pieces. So if we look at our slice is going to have a little bit of thickness. So let me put a little bit of thickness like this. And now you can see we have a trapezoid with a little bit of thickness. This little bit of thickness right here, that's going to be what we call delta x. And delta x, just like before, was b minus a divided by n. All right. So if we were to look at our cross-sectional area picture over here, at the beginning, we have a very small cross-sectional area. So this cross-sectional area looks like this. It's got a little bit of thickness like this. That's sort of one slab. This would be like A of x3 in this particular picture. And then, if you looked at the one at the very other end, you're going to have a much larger cross-sectional area. That would be A of x0 in this particular case, but that also has a little bit of thickness like this. Okay. So I hope that you could see that if I wanted to calculate the volume, the total volume of this object, the total volume is approximately equal to the sum of all of those slabs. So if I added up all the slabs from 1 to n, and I took the cross-sectional area, A of x, and I multiplied that by that little bit of thickness, delta x, then this whole thing right here, this is the area of each slab. So this is the area of each slice. Area of each slice times a little bit of thickness. In other words, this is the volume of the slice. Okay. So what we're going to do is we're going to take a limit. So the volume is actually going to be equal to the result you get when you take the limit as the number of slices n goes to infinity of this sum as I goes from 1 to n, A of x times delta x. All right. So I hope you guys can recognize that that limit is really a definite integral. So this object right here is really a definite integral. So if the cross-sectional area of the solid is given by A of x, and the axis of the solid is aligned with the x-axis, then the volume of the solid is going to be given by the following definite integral. Our volume is going to be equal to the limit as n goes to infinity of the summation as I goes from 1 to n, A of x. Really, it's probably a xi star, if we're going to be precise, times delta x. But the key point is that we're going to end up with a definite integral. And the definite integral is going to be the integral from a to b times A of x dx. So this delta x, that's like a little bit of thickness. So delta is the Greek letter for d. Sigma is the Greek letter for s. Okay. So this is the key formula for us. Let's highlight that guy. This is how we're going to calculate volume. and we are going to look at an example together in class. Take care, everyone.